So it's a pleasure to try to summarize and then lead into a little bit of what some of the challenges are, open questions. This will also lead into the discussion at the end, generally in the area of galaxy formation, structure formation. So to provide some context, I think it's useful to remember what really has been the real success story in our understanding of galaxy formation and galaxy evolution has been understanding the connection between the underlying dark matter distribution and the distribution of galaxies. So in some ways, the parts of the problem that we understand the best are that relatively simple models that associate the properties of galaxies and the distribution of galaxies with dark matter. So both into determining the statistical properties of galaxies and in relating, stellar masses of galaxies, star formation rates of galaxies to the underlying properties of dark matter halos. Those types of ways of thinking about the problem have been extraordinarily successful. And they've been successful largely because it turns out, at least so far, we've been lucky in that a relatively simple dark matter model called dark matter does a good job of reproducing what we observe in terms of large-scale structure and large-scale gravitational evolution of the universe. The challenge comes really when we move to scales inside galaxies where the baryons no longer continue to track the dark matter, where you really have to start to worry about things like star formation and supernovae and AGN and black holes. And there, I think, kind of broadly labeled with the term feedback. And there, I think our understanding is much poorer than our understanding of, say, the relatively large-scale distribution of galaxies. And that's true primarily just because understanding these baryonic processes is much more challenging, has proven to be much more challenging than n-body simulations, for instance, of large-scale structure and dark matter alone. And one way to think about this challenge, for those of you who don't think about galaxy formation and structure formation a lot, one way to think about this is that we know empirically that in most galaxies, almost all of the mass that at some point gets pulled into the galaxy by the dark matter potential well ends up actually being blown back out of the galaxy in the form of outflows driven by star formation and possibly by active galactic nuclei. And these are just some examples. This is an HST image. This is an X-ray image showing the galaxy scale outflows driven, in these cases, by star formation. And so it's understanding the properties of these outflows observationally and theoretically. That's really where a lot of the challenges are in understanding galaxy formation. At the kind of purely empirical level, right, so Dan talked to us about observations of galaxies now at a redshift of 12, and we also have observations in the local group of galaxies that have luminosities of less than 1,000 times the luminosity of our sun. This is the Segue 2, the smallest of the dwarfs in the Milky Way's halo. So we actually have an amazing empirical kind of zeroth order description of the galaxy population going from very high redshift, what's the luminosity function, what's the mass function of galaxies, the star formation rate function of galaxies from a redshift of, you pick what number you believe, 8, 9, something, to low redshift. We have a growing understanding of the dwarf galaxy population of the Milky Way halo, and the real challenge, and this is where the field continues to debate, as you heard about in the talks, is really understanding which of the many different clever physical processes that people have thought of that may shape the galaxy population that we see, which are actually the most important ones. And that's something where there's by no means consensus. So I thought I would highlight 3 particular areas that I think are likely to be challenges and areas in which there's going to continue to be a lot of interesting work, both is and will continue over the next 5 to 10 years. And these are just 3 examples, some of which are things that I work on, some of which actually aren't things that I work on. So I'll talk a little bit about these, and then that'll lead into the broader discussion that we're going to have afterwards. So first, I think, is a question that hopefully also came up, it's not there anymore, but came up in the dark matter section, and probably will come up on Friday as well, is the interplay between using observations of galaxies to try to understand dark matter and dark energy, and likewise, do we understand dark matter and dark energy now well enough that we don't have to care about it when thinking about galaxy formation, because that's kind of the least of our worries. The baryonic processes are much harder to model. They're better understood in some sense, but much harder to model. And I think there's a good example of this is given by the work that's being done by many people on thinking about the kind of shape of galaxy potentials, and in particular dark matter potentials, in the cores of galaxies. So there's a set of problems that have been identified in the central parts of galaxies where the predictions of these beautiful dark matter only simulations, like the Millennium simulation here, those predictions, which do very well for a large-scale structure, start to do less and less well when you get into the central parts of galaxies. And for instance, one version of this problem is that the dark matter simulations of collisionless cold dark matter predict density profiles which continue to rise rapidly to the smallest radii in dark matter halos. And at least in some observations of dark matter-dominated dwarf galaxies, for instance, there are indications that that isn't the case. The dark matter density doesn't continue to rise to small radii. And so one class of explanations is that maybe that's telling us something profound about dark matter. For instance, that there's actually effectively a collisional cross-section, self-interacting dark matter. So this is work by Annika Peter, James Bullock, and others, showing that if you pick the collisional cross-section of dark matter just right, you can produce density cores and at least not grossly violate the other constraints we have about the statistical properties of galaxies. But there's another explanation, which a number of groups have argued for, which is that, of course, in the central parts of galaxies is where you worry a lot about the baryonic physics and what is the effect of galaxy formation on the distribution of dark matter. Maybe the collisionless cold dark matter simulations aren't the right thing to be comparing to. So for example, this is work by Fabio Governado and his group showing that ejection of material from the central parts of galaxies in the galactic winds that we see in these images, right, that can affect the dark matter distribution and produce a chord dark matter distribution, even though a collisionless simulation would produce something like this. And it's completely unclear at the present time, I would say, whether to know which of these are right. It actually looks like, so we've done simulations of something similar, and we don't see the kind of cores that Fabio Governado finds. And so that means that whether or not you get this core depends on the details of how you model the stellar feedback. So it's not clear that it's even robust, that the baryonic physics has this particular sign in affecting the dark matter. And if you think about the history, right, of using observations of galaxies to infer the presence of dark matter and dark energy, the examples that we remember, the inferences of dark matter from rotation curves and clusters and the inferences of dark energy from supernovae, are the cases where the baryonic physics was not so complicated that it really messed up our ability to infer the dark matter. And it's unclear going forward in the next 5 or 10 years, which of the many observations that people are doing are really going to point towards interesting physics in dark matter versus an incomplete understanding of the baryonic physics of galaxy formation. And I think, personally, I think this is just a hard problem. I don't have an answer, but this is clearly an area where there's going to be a lot of work, and breaking the degeneracy between these two ideas, for instance, is very non-trivial. So a second area in which I think personally there's been a lot of interesting recent work, and there's going to continue to be, is in understanding the kind of hot halos or the hot atmospheres of galaxies, which are one of the central ingredients to our understanding of how galaxies form. And this is connected to something that's kind of loosely called the circumgalactic medium. So for those of you, again, who don't think so much about galaxy formation, this is kind of the outskirts of galaxies and where galaxies start to interface with the ambient intergalactic medium, like what you see in the Lyman alpha forest. So the reason this is important is that these hot atmospheres of galaxies are a probe of how gas accretes into galaxies, which is the way that you fuel star formation, black hole growth, galaxy growth, et cetera. So this is an example of a simulation by Nagai, Kravtsov, and others. So this is showing kind of on a scale of the virial radius of a galaxy, the temperature of the gas, and the arrows are velocity vectors. That's not particularly critical. So this is a relatively massive system, like a group or a cluster, where the gas accretes in, goes through a virial shock, and heats up to high temperatures. And then in the inner parts of the galaxy, the densities in the inner parts of the group or cluster, the gas densities are high enough that the gas cools rapidly, and that cooling can then generate cold gas, like in fact we saw in the earlier talks that you actually see at the centers of clusters, that cool gas can then fuel galaxy formation, star formation, black hole growth, et cetera. And so we think this same basic process, gas accretes in, goes through a virial shock, cools to fuel galaxy formation, black hole growth, et cetera. This is kind of the key ingredient in our thinking about galaxy formation. And the kind of details are, how much gas remains in this hot state, or we think as you go to lower mass galaxies, cooling becomes more and more rapid, and so there's less and less gas remains in this hot atmosphere, and instead it quickly cools onto the galaxy much more rapidly than in galaxy groups and clusters. So a galaxy like the Milky Way has a comparatively less dramatic hot halo than a galaxy group or a galaxy cluster because cooling is much more important. And there's a long history of trying to look at this from X-ray observations, coming at it really from the point of view of galaxy groups and clusters and pushing down lower and lower in mass where you can still see some X-ray observations. And so I'm not going to go through the derivation, but there's a simple prediction, which is that if baryons always follow dark matter, then the X-ray emission associated with Bremsstrahlung, just free emission of the hot gas, should scale like the virial temperature of the halo squared. And this is then a plot showing, forget about the lines, this is a bunch of theoretical lines, just this is a compilation of data, that's what matters here. This is X-ray luminosity versus temperature. So these are groups and clusters, and then down here is really more the scale of individual massive elliptical galaxies. And at high temperatures, which are massive systems, you indeed see luminosity scales something like temperature squared. But as you go to lower mass systems, lower temperature systems, you don't see this simple baryons follow dark matter self-similar story. Instead, there's a significant deviation. The luminosity drops much more rapidly with temperature than this simple scaling argument suggests. And this has been known for a long time, and there's actually a lot of different reasons why the baryons might not follow dark matter and might preferentially not follow dark matter as you go to smaller and smaller mass systems, groups, galaxies, rather than clusters. The most immediately important is cooling. So as I already mentioned, radiative cooling is comparatively more important in lower mass systems. And so maybe that suppresses the amount of gas that's in this hot atmosphere, producing this non-self-similarity. Maybe it's star formation, maybe it's feedback, supernovae, heating up the material, decreasing the density, decreasing the X-ray flux. Maybe it's AGN, maybe it's cosmic rays. Lots of different physics could be involved. Another way to look at this is that when people have tried to reconstruct the baryon fraction within a dark, 2 minutes, okay, when people try to reconstruct the baryon fraction within a dark matter halo as a function of halo mass, what you see is that in clusters, the baryon fraction is comparable to the cosmic baryon fraction shown by this span right here. But as you go to lower and lower mass systems, the baryon fraction seems to actually drop below cosmic by an interesting amount. And so there's two sets of new observations which are providing new insights into this problem. And I think it's not quite clear at this point how to relate what we've learned from the X-rays to what we're learning from these new observations. So one is that Planck measurement of the SZ signal. So the Sunyaev-Zeldovich signal is basically a measure of the total thermal energy of hot gas in a dark matter potential well, actually shows a nice self-similar scaling as low down in mass as they can go, which is, kind of getting to the most massive galaxies. And so this self-similar scaling is not at face value entirely consistent with what we think we know from X-ray observations. The simplest explanation for that difference is that the X-ray emission scales like density squared. The SZ signal is basically pressure, so it's linear in density. And so the SZ cares more about large radii. The X-ray is more sensitive to somewhat smaller radii in the galactic halo. And so maybe whatever is producing the non-self similarity in the X-ray emission is just somewhat gentle in that it doesn't blow the gas completely apart, hence affecting the large radii that the SZ is sensitive to, but it really is affecting intermediate radii where the X-ray emission is most sensitive to. The other observational breakthrough, which is teaching us a lot about the hot halos that fuel galaxy formation, is continued probes of cool gas embedded in this hot ambient halos, very much like what Norbert talked about in the context of clusters, but again now pushing down to the scales of galaxies rather than groups and clusters. So there's now evidence for very large masses of oxygen within the virial radius of star-forming galaxies, seen in absorption with HST UV observations. And there's evidence for quite high covering fractions of cold, optically thick hydrogen seen in quasars and Lyman break galaxies. So these are, I think, areas where the observations are really pushing our understanding of how gas is getting into and out of galaxies. Okay, so the last thing I'll just end by mentioning what I think most of the people who work on computational galaxy formation would agree that the real frontier in our understanding of galaxy formation numerically is trying to better model the interstellar medium, the process of star formation, the effects of supernovae and stellar radiation, and the effects of AGN on the galaxy formation process. And this is an extremely challenging problem. I think it's fair to say that most of the things that simple galaxy formation models have trouble explaining, people invoke stellar or AGN feedback in some way to resolve the tension with models that don't include stellar and AGN feedback. Things like the low baryon fraction in stars, the lack of cooling in clusters, et cetera. And I think from my perspective, the challenge that this raises is just how well do we really have to model the interstellar medium to make predictive models of galaxy formation. And I don't know the answer to that. I think that's a really hard problem. And this is something that a lot of the community is grappling with at the present time. So just to give you a feel of the range of ways that people approach this problem, These are two simulations that we did of the central regions of a galactic nucleus where you might form a black hole, you might grow a bulge. This is a model in which there's no stellar feedback and you let the gas cool to 100 Kelvin. This is a model of no stellar feedback where you don't let the gas cool below 10 to the 4 Kelvin. And these bracket kind of the extremes of how people approach this problem. In this case, all the gas cools, forms these dense nuggets. The dense nuggets turn into stars, spiral in to form a bulge, and potentially grow a black hole. In this model, the gas doesn't collapse under its own self-gravity. It forms spiral structure. Gas gets funneled in along spiral arms to fuel a central starburst that grows a bulge and grows a central black hole. These are two very different physical models for how you might fuel the growth of the central part of a galaxy. And knowing which of these is right means you have to really be able to follow how much gas collapses into these dense clumps versus how much gas stays in a more diffuse phase of the interstellar medium. And that's basically the problem of understanding star formation in the interstellar medium. But now we have to do that in the context of large-scale structure, in the context of galaxies as a whole. And I think that's a very challenging problem. And it's not at all clear that the simplified subgrid approach that myself and other people are taking to this problem is really going to be good enough to make the models predictive, where you can actually start to believe them vis-a-vis observations. So I'll just end with these challenges, and then I'm happy to discuss these, and we can also move on to a broader discussion of additional questions that some of the other speakers suggested we talk about. So thanks.
Concerns that's been raised in recent years is the effect of particularly AGN feedback, but other galactic processes, on putting baryonic biases into weak lensing surveys and thereby compromising the attempts to measure dark energy equation state and all of that. What's your view on how serious a problem this is, and what do you think can be done to mitigate it?
So I have to admit, I have not thought about this in the context of weak lensing in particular. So I don't have a well thought out answer. So is the concern that the baryonic physics actually modifies the potential?
Well, yeah, will modify the effect on the structure,
yeah,
and the galaxy formation out to very large distances, and high L. And Zentner, I think, is the person I've heard talk about this,
yeah.
and others may know more about it, but it seems to be relates.
So I think it's true that on large scales like the Lyman alpha forest, for example, models with just gravitational physics and not much feedback physics do an excellent job at reproducing what we see. And on, this is interestingly suggestive that some kind of simple self-similarity might actually do a decent job for hot halos, even down to interestingly low masses. Whether this affects weak lensing in particular, I don't want to comment on because I haven't actually thought about the issues in the weak lensing context. So.
Yes. The next question. Elliot, you mentioned about the, thank you, at the beginning of your remarks about the importance of galactic outflows, particularly at a higher redshift. So my question is, if you just look at the Milky Way as a typical disk galaxy, the star formation rate has basically been constant since the beginning. And right now we don't have much of an outflow, so why would we have had an outflow then?
So that's true, but the Milky Way is also, at a redshift of 1, the Milky Way would not be a typical star-forming galaxy. A few solar masses a year would be pretty low. So I think it's true that at the Milky Way's star formation rate, it's not clear that there's a substantial outflow. although at least I would say there could still be there could be an outflow with an outflow rate comparable to the star formation rate, right? I think that's not ruled out. The Milky Way also, remember, is just coincidentally in terms of the stellar mass relative to the cosmic baryon fraction, the Milky Way is kind of at the peak of star formation efficiency. So it is the mass scale where the need to get stuff out is the least, although there's still the kind of efficiency of galaxy formation, even in the Milky Way, is relatively low relative to the cosmic baryon fraction.